Thanks a lot, Christoph, and thanks for the introduction. I would like to start by thanking the organizers for inviting me to give this talk. It's a pleasure for me and an honor to present here at the NOLCOS. And I would like to thank you all for attending. So what I'm going to present today is a bit of work that I've been doing in the past, say, 15 years on Lyapunov-based techniques to assess performance and stability of control systems involving resets. So we have a controller whose state is sometimes reset to a quantity. Notably, most of the talk will be resetting to 0. And the outline of my talk is at the top of my slides. I'm going to start by talking about the Clegg integrator idea, which dates back to more than 50 years ago. And then I'm going to move on to a generalization of that, which is called first-order reset element. And that's still a first-order system, but it's not an integrator. And we're going to try to generalize to higher-order resets. And if time allows for it, I'm going to talk a bit about friction compensation using reset control, which is a kind of a different thing from the rest of the talk, but still is about reset, and I think it's insightful, especially once again from the Lyapunov viewpoint. And can you guys hear me well? Is this like making, right, is that okay? Yeah? Okay, thanks. Okay, so let's start with Clegg integrators, and in particular, what we're going to look at is very, very simple feedback loops with just a first-order system, okay? So a lot of what we're talking about here is simple. Let's try to make it intuitive. And let's go back to 1958, when analog controllers were around. And so Clegg in 58 said, okay, so if we have a PI controller, which involves an integrator, let's try to add a nonlinear nature to it to perhaps improve convergence, performance, phase lag, or something that was measured back then in terms of the linear tools that were available. And in particular, the analog version of an integrator with an op-amp is exactly this, right? So the differential equation is this one, and if this is minus xc and it's the voltage across the capacitor, that's the integral of the input E. And we're looking at an error feedback interconnection, so to speak. So let's consider the input of this guy being E, as in, you know, like the tracking error or something. So what Clegg did, he said, oh, you know what, let's split this in two parts, an upper and a lower part, and the novelty is these diodes. So if you look at the upper part, the voltage here, whenever it's higher than the input voltage, will, you know, cause conduction in the diodes. So the voltage across this capacitor will discharge. That's a reset to 0. And the same will happen here if this voltage is very low. As a consequence, all and only the positive part of the output is stored up here, and all and only the negative one is stored down here. And in particular, it's impossible for this circuit to have opposite signs at the input and the output. So the resets enforce this very peculiar property of ensuring that input and state, or input and output, have exactly the same sign. Now, if you represent that in the phase space, or like in the input state space, and let me reverse the E, because we're anticipating a negative feedback interconnection, then what you get is that within this set, where XC and E have the same sign, solutions will be flowing, and they will flow according to this differential equation. That's, you know, the dynamics of the integrator. Whereas if solution starts here, they will reset they will jump according to this difference equation. So XC will jump to 0. That is, jumps will lead us to the horizontal axis, right? Now, this is a hybrid system, and in particular, we call this F the flow set. So that's, you know, this set here, and the J, where jumps occurs, is the jump set, right? So if you think about evolution of solutions following, you know, the great work carried out by Thiel and co-authors in the past, say, 15 years, you could put a timer in the solution that is going to be continuous time, which will increase as solutions follow the differential equation, whereas there's a counter counting the jumps that will only increase as solutions follow the difference part. So if we rewrite this with that context, essentially we will look at solutions as having a domain which is across product between continuous evolution T and discrete evolution J. And in particular, the differential equation only relates to T, of course, whereas the difference equation will experience an increase of J, which is, of course, discrete, right? Because that's a discrete time part of the dynamics. Now, if you think about this type of representation, everything becomes pretty much clear about what's going on. The solution either flows and then T grows and J stays constant, or it jumps and then T is frozen and J counts the jump and it grows. And in particular, if these two sets, F and J, are closed, because of the regularity of this data, if you establish stability of some interconnection of this guy to some, say, linear plant, that stability that you establish is robust, okay? So that's a nice result that, you know, all the group has been working on and is well summarized in their 2012 book. Now, I would like to emphasize what's the advantage of this. And we've been talking about this with Andy Thiel and Dragan Nesic during this, you know, trip to Australia back in 2004 during the Asian Control Conference, where a lot of these preliminary ideas came up, and much of this talk talks about that stuff. What is interesting is that back in '58, Clegg was saying in his paper, my circuit resets when E is equal to 0. And this was somehow carried over in later years by Horowitz in the 70s and so on and so forth. And people have always been thinking about the resets as being this thin line. Now, the problem with that, especially when you're looking for Lyapunov certificates, is that solutions from here for this model will have to flow. And so if you impose a flow condition on the Lyapunov function, which we'll clear later, that's overkill, actually. You can see that you will have to impose it everywhere by continuity. And also there's another bad issue is that with this thin line, detecting when to jump requires introducing extra zero crossing conditions, which are completely wiped out by this more accurate description of the very nature of the analog circuit. Because the analog circuit had to work somehow, like it can't have a zero crossing detection embedded into it. So anyway, like more specifically, let's look at a you know, solution to this guy. So let's take the input E as being this sinusoid. Then the output will integrate. And so the T variable, this is the domain, right, of the solution. The T variable will increase. As soon as the output and the input have opposite sign, there's a reset and the timer jumps, right? The J is increased. And of course, the XC is reset to 0, and there's another integration, and so on and so forth. So this is the graph of the solution, right? Of the solution in terms of the state of the Clegg integrator. And the domain, of course, is this subset of the TJ axis, plane, sorry. Okay, so what can we do with this? We can apply a lot of, you know, very useful Lyapunov theory, but perhaps the simplest thing I can tell you is, let's say you have this system, and now perhaps there's already an interconnection, you know, of the Clegg integrator with a plant. If you want to establish stability of the origin, what you could do is you could search for, like, say, a differentiable function V, or say a Lipschitz one, which satisfy what we call the sandwich inequality. So you sandwich V within quadratic bounds, so that's, you know, positive definiteness and radial unboundedness. And also, you have a flow condition of the typical continuous time type. So V dot has a negative quadratic upper bound, but you only need to enforce that in F. So that's, you know, an important message. So F is now half of the state space. And then you also need to enforce a jump condition. That is, when the solutions jump, you know, they should lead to a decrease of V, as in this negative upper bound again, but only in J. Okay? So we call this the flow condition and the jump condition. And when they're satisfied, then you have a nice exponential bound. Now, one thing I would like to emphasize is this exponential bound has T plus J as a generalized hybrid time, because this is a hybrid system. Okay? Okay, so let's use this theorem. Let's try to interconnect the Clegg integrator to something. Now, historically, the easiest thing you could interconnect it with was an integrator. So you take an integrating plant, you connect it to the Clegg, which is an integrator itself, and then you look at solutions, again on this phase plane, right? So let's start solution with x equal to 0, initialize the controller at 0, and xp is equal to 1. What will happen is that solutions will flow along circles, right? Why? Because the closed loop characteristic polynomial is s squared plus 1, right? So the linear response is an oscillator, right? Linear oscillator. So solutions revolve, will reach the boundary of J, and here a reset must occur to the horizontal axis, that is to 0, right? So the Planck state looks like this. It evolves, here there's a reset, and then puff, continuous evolution at 0. So flowing at 0, right? Now let's look at a graph of this Planck state, right? The solution flows, it reaches 0. Oh, and then here it actually jumps forever. It doesn't flow forever. So this is one extreme case. 0 is actually a point which both belongs to the flow set and the jump set. So there's at least two solutions, right? One flowing forever, one jumping forever from 0. Actually, there's infinitely many solutions. They can jump and flow whenever they want. Still, the origin is an equilibrium point because all those solutions are constant, even though they don't have the same domain. So that's beautiful. No overshoot, you know. I like this. But there's a catch. It's not really true because there's another bad solution. If we start here, we're at the boundary of J, and there's another solution which can jump, and it jumps forever right here, and it gets stuck exactly at the boundary. So if you're looking for a Lyapunov function certifying stability of the origin for this system, there's no way you can get it, because the origin, at least for the simplified model that we built, is not globally attractive. So how can we do that? And that's what we've been thinking, like how can we rule out this bad solution? There's two ways, okay? So one is called time regularization. And it essentially comprises starting a timer and inhibiting resets after each reset for some continuous time rho. So you wait rho, and the solution will flow and get away from J so that it can continue as I showed you before. And that works. The other one is space regularization. That means we can twist the sets in such a way that the jumps will map to the interior of F, so away from J, and a second jump will not be possible. What does that mean from the Lyapunov viewpoint? Well, for time regularization, you have to accept that because of this timer, solutions may overflow outside of F. Okay, and we'll get back to that in a sec. And then in the other case, the problem is more subtle. So you could get space regularization by twisting, you know, the sets in this nice homogeneous way. But the problem is that to make sure that you jump to the interior of F, you really have to be careful about the additional direction. So we're looking at the plane here, but let's already think about what to do with higher order plans, right? So this axis is a lot of directions. And for sure, you will need information about the whole state to comply with this type of requirement, which is kind of an overkill, okay? Anyway, so most of this talk we will be talking about time regularization, and I would like to introduce a family of systems that is described by this type of logic and that generalizes the Clegg that I showed you so far. So essentially, we're looking at sets F and J, but the sets where the solution is allowed to flow or jump is a bit more sophisticated and depends on the timer. So we introduce the timer tau, which is reset to 0 after each jump, and we are essentially not allowing jumps by definition of D whenever the timer is too small. So the timer has to be larger than or equal to rho. The nice feature about this is that after each jump, there will be rho flowing time. So we will have what we call persistent flowing, right? The bad side, though, is that because we are, you know, inhibiting jumps, we must allow for flows even though X is not in F, which is what you're seeing here, right? So essentially, we're allowing flow when tau is too small in places that we cannot predict. And that's kind of a problem. So we might have this overflow. Well, the good news, though, is that at least for these systems, we can prove things that are similar to, you know, linear systems, like equivalence between local asymptotic stability of the origin in the X direction, global exponential stability, LP stability from D, so D is a disturbance, ISS. Okay, so we can use those results. And let's see, if we go back, oh, actually, there's another thing I wanted to tell you. Another advantage of having persistent flowing, though, allows us to do something which is fairly reasonable. If we're looking at reset control over continuous time plants, we are more interested in performance metrics that are based on continuous time only. So one thing that we will study and characterize is the so-called T decay rate, which is having an exponential bound on solutions, which differently from the stability theorem that I showed you before, does not have J in it. So we really insisted that it is continuous time to tell us how long it takes for the solution to decay exponentially. And that's convenient from the point of view of a continuous time plant. And similarly, if we look at some kind of L2 stability or finite gain L2 stability, we would be, happier to only consider a norm, an L2 norm of D, which only involves integrals, okay, as opposed to hybrid norms that actually involve also sums in their definition, because they are like the generalization of their continuous time and discrete time counterpart. So we're going to be looking at these properties in the next theorems. And I don't want to overwhelm you with theorems, but there's one theorem which is so straightforward, I should really mention it, right? So when you do this and you look at that homogeneous or partially homogeneous dynamics I showed you before, you can actually come up with quadratic Lyapunov functions. Quadratic Lyapunov functions for, say, this TL2 stability will give you the bounded real lemma. And everybody knows about the bounded real lemma, right? So if you impose the bounded real lemma, then you get a nice L2 gain. I mean, you need to be a bit careful. When jumps occur, you need a suitable jump condition. That essentially says that V does not increase. And also, you may take advantage from the shape of the flow and the jump sets, which are parameterized by M, using some kind of S procedure, right? So you're only imposing this property in F and only this property in J by way of those, say, nice additions to your linear matrix inequalities. These are, by the way, linear matrix inequalities in the unknowns. Okay, so I want to emphasize one thing about this theorem. This less than or equal is tricky. It's because G, at least for the Clegg integrator, only resets the controller state, right? So you cannot reset the plant state. So you cannot possibly expect here some negativity which is on all directions. So this is really important. If we insist on negativity here, we'll never be able to solve this. Turns out that quadratic conditions are quite conservative in general, and we need to resort to more sophisticated conditions, like this piecewise quadratic condition, where now we're really insisting on the, first order reset controller and its input-output space. So this is its input-output space. The other direction of the plant will be all concentrated at the origin. I don't want you to digest this, but I want to show you nice level sets. So this is the rough idea. In the flow set, you have a bunch of quadratics that are patched. And in the jump set, you only have one quadratic function. And then you have a generalization of the previous theorem. Let's say you have a flow condition, you have a jump condition, and then you have some continuity conditions and some overlap conditions related to this, overlapping conditions that I mentioned when I introduced time regularizations, right? I told you need to ensure that you do well when solutions overflow, right? So let's go back to the Clegg integrator. So we're back to, we're comfortable with these things. Here are the solutions. They revolve, they reset, they revolve, they reset. So first of all, there's no quadratic Lyapunov function. You can actually prove that. So you cannot find a quadratic Lyapunov function that certifies global asymptotic stability of the origin, which is exponential because of the other theorem, by the way. Anyway, so we can build a piecewise quadratic. You see how it comes out? This is the level set. It's kind of interesting to say that there's a lot going on in the flow set, second and fourth quadrant. This is a really simple function on the J. And again, I'm going to go back to the original thing I told you. Recognizing that the Clegg integrator resets only in half of the state space is fundamental to start talking about Lyapunov functions. And you see that here. So this part is easy. And it's easy because we recognize that the circuit resets over there, okay? And also, you can estimate the L2 gain. And as you increase the number of functions, you get better and better. OK, so the last thing I want to mention about this first part of my talk is that we were tempted to say that for this system, we only had non-convex Lyapunov function. This is a non-convex function. But recently, we've been looking at what is called the mid of quadratics. So you take 3 quadratic functions, and you look at the middle one. So that's a CDC paper that's going to be presented by Matteo, a PhD student. And with the middle one, you can get a Lyapunov certificate for this feedback, you know, the Clegg integrator with an integrating plant. Now, of course, this is non-convex. But the good news is you can easily make it into a convex one. So there's a simple twist. And so it's a convex one. So there exists convex Lyapunov function. I like playing with Lyapunov. OK, I'm sorry to bore you with all these pictures. Anyway, so let's move on to the second part of the talk. And let's see how we can use now these, you know, reset controllers in some more practical things. And in particular, let's extend the ideas of Clegg to something more sophisticated. So I'm back to the previous slide. You've seen this already. And let me think about this as some linear filter with an eigenvalue at 0. So we can add this eigenvalue, and the dynamics will become like this, right? And that's what Horowitz proposed in the 70s. Except Horowitz insisted on this AC being negative, being not positive. For the Clegg, it's 0. But he insisted on stable first-order reset elements. Now, what we did by looking at these interconnections was to say, oh, no, but let's go beyond that. And indeed, you can prove that if the plant is minimum phase relative degree 1, so let's say a simple plant, but still higher order, then you can crank up the pole. That means making this guy arbitrarily exponentially unstable, and so also the closed loop, or crank up the loop gain, or both of them, and you obtain eventually global exponential stability of the reset feedback. So let's look at the trajectories. Let's stick an integrator here once again, just for simplicity. And then, you know, let's pick the loop gain equal to 1 and increase AC. So for a very negative AC, you don't even reset, okay? Now, for AC equal -1, the linear response would be the black. The blue is the reset. Deadbeat, again, you've seen this on the Clegg integrator. It's the same old story, right? And in particular, now if we increase this guy, we start seeing exponentially diverging branches which are reset in a deadbeat way. So that's beautiful. That's the main message I want to deliver today. We can introduce exponentially diverging transients on stabilizing controllers. It's really cool. I don't know how useful that is, but maybe it is a bit. So let's look at an application. Oh, no, but first let me actually show you what you get. Oh, no, I forgot to tell you something. Sorry about that. So I'm going to go back one. I just wanted to say that we also have this nice result saying that in the planar case, the gain from D to Y actually goes to 0, which is quite evident if you look at this, right? You see how faster and faster these transients would be. So if you think about this initial condition as the effect of an impulsive disturbance, you realize that this gain must be going to 0, right? And we actually prove that, but only for scalar plants. So let's apply this thing, and in particular, let's apply again the piecewise quadratic construction to a second-order plant. Comes from the literature of resets, you know, work done by Hollott, you know, in the late 90s and early 2000s. So with this one, this is the type of Lyapunov function that you get when you project on the input-output space of the Clegg. Remember here, the state space is three-dimensional. And the gain actually goes to infinity if you only look at the linear without resets, and then goes to 0 asymptotically as AC grows. Of course, we don't have a proof of that, okay? We only proved it for scalar plants. But still, looks interesting. Now, if we want to apply this experimentally, the first problem we encounter, and that's another message for today, is that by introducing resets and resetting this guy to 0, the U will go to 0 every time, and that is, in a sense, if we had an integrator, we will lose the internal model properties of, you know, the original linear feedback with constant references. And that's actually overkill. So you will start seeing solutions that keep oscillating. So one way to reintroduce the internal model in a clever way would be to introduce an adaptive feed-forward. Okay, so the feed-forward here is, some function here that may also include some nonlinearities that we know, will happen at the steady state, times some parameters alpha, which are not adapted during flow. They are kept constant during flow, and they are adapted at jumps based on the value of the feedback state. So the feedback state, in a sense, captures the information about the previous errors that we made. And it turns out with a scalar plant, you can tune the gain lambda of this adaptation following some kind of Ziegler-Nichols type of approach. So you take the system into oscillation for a large enough lambda, and you get something similar to the green curve here, a bit larger. You divide it by 2, and you get some sort of deadbeat, kind of convergence of these parameters. Now, if you go too slow with a very small lambda, this convergence will be a lot slower, okay? And this is an EGR experiment. It's an exhaust gas recirculation valve, and we're doing position control here. So that's something I did when I was visiting Linz, next door from here in 2011. And in particular, the EGR valve in a diesel engine, it connects the intake to the exhaust manifold. And it's got a big problem. Here it is. It's that the exhaust is on this side, so the difference in pressure pushes very strongly the valve to the closing direction. And as you're trying to open it, these disturbances are very high because of the high pressure difference. And then the pressure drops. So this is kind of tricky. As a matter of fact, in my old Punto car, I could hear the EGR valve banging when I was accelerating, because that's Fiat, right? So everybody knows Fiat. So I was getting, I was accelerating, and I could hear from the engine compartment, and this was really the EGR valve banging, right, on its end point. Anyway, so we don't have much time here, but I want to show you how the feed-forward nicely converges, right? So this would be the function when alpha converged, and you see all these steady-state input-outputs. This is like a lot of stiction on the valve. Still, this does quite well. These are lab experiments. The valve is mounted on a lab, and this kind of tells you what's going on when you train, this feed-forward. You see at the beginning when the alphas are very bad, the output has a lot of oscillations, and of course the input does the same. And I'm not going to comment too much on this, but I want to show you a step response after the alphas have converged. And I'm very happy about this. So you see the red curve is the reset controller. And you can see how fast it is as compared to the best PI we could tune for this step value. So we really concentrate on this. I tell you, if we increase the bit gains of the PI, we would get steady-state oscillations because of unmodeled dynamics and stuff like that. So this was really the best we could do. And you see how fast this is, and I really want you to notice the exponentially diverging input. I really like this exponentially diverging input. It's one of the main messages today, right? So we're stabilizing, set point stabilization with this guy. Now, the time optimal that you see here, it took us a day to get an experiment like that. Of course, it's extremely unrobust. So we tried to tune the length of the 3 pulses. We eventually got one, and that gave us, the reference value, because we could only get it once, right? So that's it. Okay, so that's for set point regulation. And there's some generalizations that we're trying to achieve, and I'm going to show you something which is extremely preliminary. So we need to do a lot of work on this. But I still want to tell you one thing. Like, if you're doing reference tracking, one way to obtain that, which is perhaps cheating, is to use the derivative of the reference, at least when the plant is first order. Otherwise, you need, adaptive right inverses, and then for adaptive right inverses, how many derivatives you get will depend on the relative degree, right? But then it gets a lot trickier. So far, we tried it with this type of setting, and we applied it with a company close to Trento that works on power split transmission systems of highway vehicles to the current regulation, current tracking in the valve that operates on these transmissions. Okay, so actually this filling, problem for clutches is a big problem. I've seen a paper here at NOLCOS on that, so that's interesting. And you know, one aspect is important is current regulation, is you need to get really the current you want on the valve. And you see what happens here. It's the same as before. The alphas are adapted through like an experiment, and the output current, which is the blue, is really bad at the beginning, right? The reference is the gray. But it's very, very good at the end once the alphas have reached their steady state. And what's happening is that if you look at the input, the feed forward, which is the blue, is very different from the total input. The feedback action is down here. Sorry about the scale. The scale is wrong here. I apologize for that. It should be divided by 10. But anyways, you see these two scales are the same. You see at the beginning there's a lot of feedback action. At the end, there's almost no feedback. You know, the input is essentially feed forward. And that's beautiful. Feedback is still acting, and it's adapting the alphas, but it's, you know, like homogeneously fading away. And that's the nice thing about homogeneity of these systems, right? Okay, so, I'm done with the main messages. So everything else that is going to come up now is further discussions where, you know, maybe trying to go beyond this first order, you know, controllers. But it's already like good that maybe I, you know, fascinated you about this exponentially unstable branches and so on. Now, there's, however, one intuition I would like to share with you, which is related to looking at this Clegg integrator and saying, look how well it works, right? So, no overshoot, you reach the set point, it just stays there. What's the catch? What's the core intuition behind the fact that it works so well? And I'm going to try to convey the idea that we had you know, about 10 years ago, about generalizations of it. So let's go back to the Clegg integrator, and let's think about, say, a Lyapunov function, which is just circles, okay? So norm squared. Now, if you think about it, anywhere in the state space, you could wonder, what is the value of xc? Xc is the variable that you can manipulate. And what is the value of xc that actually minimizes your function? Now, of course, in this case, it will be 0, right? Because you're looking for the place where you're going to be tangent to the levels that's low. If the Lyapunov function was stretched, you know, from here, you would want to jump down here, okay? So for this case, the minimizer is actually 0 anywhere in the state space. So that explains why resets are resets to 0, because we reset to the minimum of the Lyapunov function. Okay, so that's my first intuition. Second intuition, when do we want to reset? So let's look at a function, Vp, which is the original V evaluated along this minimum, okay? So that's going to be the norm of xp squared for this special case, right? And then let's say we are happy whenever this function is decreasing. So in this area, that function, which is the projection on the state of the state on the horizontal axis, will always be decreasing. At this point, it starts increasing. That's when we reset, okay? And in particular, you can sort of imagine or, you know, claim that all the transient you would get beyond here is caused by the dynamics of the controller. It's not necessary for the plant, right? The plant doesn't need that, but the controller needs it. Oh, by the way, I forgot to tell you, it was written on the slide though, that he proved back in 2001, Becker and co-authors, that this feedback with resets overcomes intrinsic limitations of linear control. So here what it does, the controller is continuous, so it must continue from here. It cannot jump, right? But we can go beyond that. We reset it to 0. Why do we reset it to 0? Because we want to keep decrease of Vp. So you can do that, and you can do it in a general context, even nonlinear, and it's what we did you know, in this paper with Christophe and Sophie. And in particular, for the linear case, you go back to the same, you know, jump sets as those that we saw before. And yeah, so that's something I would like to give you as an intuition for a generalization to higher order systems. Now, we've been working a bit with this, trying to, you know, especially focus on linear quadratic functions cases, which are already hard enough. So maybe one possible controller architecture exploiting this is this one. You have a linear dynamics, maybe an output feedback from some linear plant, And then you have a supervisor with the usual sets, the ones that I showed you before, time regularization. And then, you know, whenever the supervisor's deciding to jump, the controller state jumps to this minimizer, right? Or generically speaking to Kp times xp, right? Because that's going to be a linear minimizer for the quadratic case, okay? Now, you could either design the whole thing or maybe just Kpm and rho. So if we design Kpm and rho, I'm just going to show you an example, okay? So we have a DC motor, PI controller, and we do position control. So the linear part that was pre-designed would get us this type of transient. And now let's do this trick. VP, so let's do the reverse thing. Let's not fix V and then determine VP. You can do the opposite. You can fix VP and then determine the V. Of course, you have some constraints, but it works. So let's fix VP to be the norm of the output squared. Well, that means you're eliminating overshoot. Well, you can't really fix it to be this guy squared because PP has to be positive. But you can still stretch it a lot, and you still see a little bit of overshoot here, of course. But, you know, you get this nice reset. You may do other stuff, like you might want to maximize the decay rate alpha by imposing some kind of Lyapunov conditions on the decay rate, you know, the typical A transpose P plus PA less than minus 2 alpha P, right? So the stuff that LMI guys like us, you know, like looking into. Anyway, so, you know, that's one idea. Now, the other thing that we've been looking at, which gets increasingly tricky, is to say, can we do reset H infinity design? And here, everything falls apart, of course. You know, things are never easy in life. And so we start cheating. So if we want to design everything, all the blue guys, we can do that, but we need the state. So we don't need the state of the plant for the continuous feedback. But the supervisor, that is the deciding when to jump and where to jump, needs the state. Why is that? Well, it's because of the space regularization that I was mentioning at the beginning. If you want to jump to the interior of F and get these nice properties which are embedded in this intuition, because you jump to the minimum of a Lyapunov function which is positive definite, you need the whole state. So then you could claim that you could add an observer, but it's not going to be used all the time. You only use it when you jump, right? And how do you assess the performance of this? It's kind of a messy thing. So we can do that, and we can say, oh, like if you had the state, the multi-objective goal in the design of these guys in a sort of a reset H infinity paradigm is a lot improved, and it is. But in the real system, you have to put the observer in. Now, the nice thing to tell you is that if you apply the Scherer's-like approach, you know, like the factorization of this plant order solution that was presented in the 97 TAC paper by Scherer, Gahinet, and Cigliali, you do get nice properties of PP. So that's an interesting observation. This PP is in general a nonlinear function of the elements of P. But for that specific factorization, it becomes something that you can, you know, invert by looking at the dual problem, and you still get linear or almost linear matrix inequalities with a few scalars that you need to optimize by side because of the S procedure, which is actually nonlinear. Okay, so anyway, that's it. Now, I got bad news for you about this talk that has been already presented this morning. I wanted to publicize. Oh, and let me publicize this talk that will be presented this morning at 11 by Francesco Ferrante, which talks about a new idea. I would like to share with you this new idea. I would actually like to share with you why it is so hard to implement a fully output feedback solution. We succeeded in doing it here, only focusing on exponential convergence. So we're not looking at L2 gains so far, huh? It's too hard. But what we do is what we could call freeze and play. And the idea is we have to introduce dwell time, right? So because we have to, then we better use it well. And in particular, let's freeze the controller state and the plant input when tau is smaller than rho. How do we do that? Well, xc dot will be 0, v dot will be 0, u will be v. Everything is frozen, okay? And then let's impose a Lyapunov decrease from the time we reset to the time until tau is equal to rho. We'll take care of the transient in the middle by a suitable overshoot. We don't care. That's a fixed time. And then we can come up with some LMI-based conditions again to design this, quite sophisticated control. You see there's the continuous part here, and there's somehow the discrete part here. So you need to do two Scherer change of coordinates, the discrete one and the continuous one. And everything works, except for these like two little parameters that correspond to line searches. And the Lyapunov function is fairly straightforward, but kind of interesting. It uses a lot the timer, and it is based, once again, on the quadratic stuff, right? So, but it's a bit beyond just quadratic. Okay, so that's it. I'm done. So I just wanted to finish by giving you like another bit of information on something that I've been doing, which is unrelated to the rest of the talk, but it's still reset control. And so I would like to tell you the story because I think it's fascinating. And it's how we use reset in a motion system with ugly friction effects. And in particular, the first thing I would like to tell you is what to do on a positioning system where you have friction that looks like this. It's Coulomb plus viscous. If you do PID control, it is well known that you have convergence but slow transients, okay? And that's the manipulation stage of an electron microscope in the nanometer precision that is not behaving very well. And in particular, what you can do is you can come up with a discontinuous Lyapunov function. You have to take care of a number of details to deal with the discontinuity of this function. It's especially helpful for proving convergence, but what you can do is you show that this discontinuous function is well behaved even if you introduce resets of the integral state. As a matter of fact, the dynamics looks like this in transform variables where sigma is a position and phi is sort of the integral state, okay? And yeah, it works well. There's an alpha. So notice that what you're doing, you're reversing the integral action, or like this is more related to the control input, I would say. And what you can do is then improve performance through this alpha, which is between 0 and 1. So alpha equal to 0, you get more robustness, but less performance. And so this is no reset. So these are experimental results. And as you increase alpha, you can see how faster the convergence is. The blue is the position. The red is the control input, okay? And so the last thing I would like to publicize is the recent stuff that was presented this morning also by Ruud. So it's too bad, same session, unfortunately, it was this morning, but it's okay. So this is the hunting phenomenon that you get when you add Stribeck to these resets. So the hunting phenomenon is an instability. And if you implement more complicated resets that I'm not going to comment now, you get a very nice convergence. Again, these are experimental results. Now, we're working on a draft. The proof so far is 12 pages long. It's like a nightmare proof. And I'm trying to see, can we simplify it a bit? Because like, we have another 6-7 pages showing, the theory, the theorem, the experiments. So how can we publish this? I don't know. We'll get better tools as we go along. We need to rely on Andy and, all the other great people in theoretical control. Anyway, so I would like to conclude by wrapping up. And the only thing I want to mention is that we published a survey paper that covers pretty much everything that I discussed here, except for the last part. And the publishers agreed to make it available freely for download until September 11. Now, if you don't have the time to take a snapshot, I'm going to post the slides on my website so you can cut and paste the address. I checked yesterday that you need to register on their website. That's always the case. But then you can download the paper. And especially I would like to thank, this is a collegial work, I would like to really thank enormously all the co-authors and collaborators and friends with whom I've been developing all this stuff. Exchanging ideas with you guys, it's just amazing. It's the most beautiful part of my job, which I love, and really thank you for everything. And thank you all for your attention.